All right, afternoon, ladies and gentlemen. This is the beginning of our chapter 4, looking at mostly rational functions, even though we get into some conic sections a little bit later. So you notice that kind of break this up into 3 little sections. 4.1 and 4.2 go together with our rational functions and graphing rational functions. So some stuff you might remember from last year. A new one for us, what's called partial fractions, or partial fraction decomposition. And also another new one for us, because it was not in the Algebra 2, is the conic sections. All right, so that's kind of what's coming up for the next few weeks. Let's go ahead and get started on 4.1. So today we're going to be looking at rational functions. What are they? What are asymptotes? What's their domains? That sort of idea. And some of this might be familiar to you from last year as well. All right, so first question is, what is a rational function? And you can basically look at that first word there, rational. What does rational mean? I hope every time you see the word rational, you hear me in your head going, what is the first 5 letters of rational? Okay, the first 5 letters being ratio, so they're fractions. All right, so these are any function in the form n of x over d of x. Numerator, denominator, that's why I named them that way. Okay. And n of x and d of x are both polynomials, so you're going to need to remember how to do some polynomial math, so some finding zeros of polynomials, that sort of idea that we just got done doing. You also need to note here that d of x cannot be 0, and that should be obvious because it's a fraction. We can't divide by 0. That's illegal. And then what we're going to make note of is the domain of f of x is all real numbers except the x values that make d of x equal to 0. So we're looking for zeros of the denominator, essentially, to find our domain. All right, so we're going to base everything, for the most part, off of this most basic function, what we're going to call our parent function to the rationals. This is 1 over x. So if you want to write it as 1 over x. And then what you're going to look at is what type of x value is not allowed here. Well, I hope you said 0. The domain is x equals, or does not equal 0. It's everything except for 0. And we write that in interval notation like this, going from negative infinity to 0, jump over that 0, and go up to infinity. What we're going to do now is we're going to sketch a small graph of this. So I'm going to get an x and a y axis set up here. And we're going to go out 1, 2, 3, 4. Now we're going to go up 1, 2, and down 1, 2, and left 1, 2, 3, 4. All right, so let's make a table. Some of you might even remember what this function looked like. That's good. All right, so what we're going to do here is go negative 3, negative 2, negative 1, 0, 1, 2, 3. Now, hopefully you know right now, right away, that 0 is impossible. We can't plug 0 in because we just said we couldn't. So this is an undefined term. But we can use the other ones. When x is 1, we plug that in, we get 1 over 1. Okay, so that's nice and easy. That's just 1. And then when x is 2, I get 1 over 2. Then I get 1 over 3 for x is 3. And then I likewise go the other direction. Negative 1, negative 1/2, negative 1/3. So if I was to plot these on my graph, negative 1, 1, negative 1, negative 1, negative 2, 1/2, negative 3, 1/3. Likewise in the other direction. Now, you might know what this looks like, but I want to kind of think about this as we go forward. As x gets really, really big, as x approaches infinity, I'm just putting that number underneath 1, so it becomes 1/4, then 1/5, then 1/6, then 1/7. That's never going to equal 0. So I'm never going to cross this x-axis. Likewise, if I was to put in x equals, let's say 1/2, extend this table down a little bit. When I plug in 1/2, 1 divided by 1/2 is 2. If I did 1/3, I get 3. So notice at 1/2, I get 2. 1/3, I get 3. And again, there's no way for this to be 0 at x because we already defined the domain's not 0. So this particular function is going to crawl across that x-axis there, and it's going to come up in this fashion. Sorry, I missed my dot there. Make the dot bigger so it fits. All right, and then likewise on the other side, we get one that looks like this. So you'll make a note here that this function is never going to cross the x-axis, and it's never going to cross the y-axis. And we can do all sorts of transformations like this with this, like before. We could say 1 over x minus 2. This tells me to move everything to the right 2 units. So I can move everything to the right 2 units, to the right 2 units. And look at this. We get the same function, just right 2 units. Move this stuff to the right 2 units. And again, we get this same function. Notice in this case, x cannot equal 2. So there's going to be some little line here that x can't cross. So my graph can't cross that little line, and we're going to get to that in just a moment. We could do all sorts of other stuff as well. We could say, what about 1 over x plus 1? Well, that's going to be on the outside, so it moves up 1 unit. So what you're going to need to be able to do is look at the equation, look at a graph, and match the right graph to the right function, to the right equation. Okay, so let's move on to what is that little yellow line that I just drew there. That little yellow line is what we call a vertical asymptote. In order to be a vertical asymptote, it's basically saying as x approaches that number, f of x approaches positive or negative infinity. So if we have some graph here, we usually draw dashed lines, not that little squiggle thing that I drew before. So this would be a vertical asymptote at x equals a. This is just saying my function, as I get really, really close to this asymptote, oh, it goes way up and it goes to infinity. Let's draw that a little better. As we get closer to that asymptote, it goes almost vertical. Or it could go this direction. It could go to negative infinity right here. So we're talking about as we approach a from both sides, it's approaching either infinity or negative infinity from either side. We also have horizontal asymptotes. Oh, by the way, this VA, this represents vertical asymptote, and HA represents horizontal asymptote. Okay, just so you're playing along here. All right, so horizontal asymptotes are if as x goes to positive or negative infinity, the function approaches a number in the horizontal direction. So we could have a horizontal asymptote right in here. As x approaches infinity, the function is approaching this line, this dashed line. And likewise, we'd approach from the other side as well. This would be a horizontal asymptote at y equals b. B is just a number, doesn't matter. In this case, it kind of looks like y equals 1. But notice here in this particular graph, I also have a vertical asymptote at some number as well. So for this particular one back here, this one has a, if you want to note this, this has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Right? Note, never crossing the horizontal, never crossing the vertical. Okay, so that's what they are. Now let's kind of go and figure out how to find them. Okay, vertical asymptotes are the easiest ones. Vertical asymptotes occur when you get zeros in the denominator. So if I gave us a function like f of x equals 1 over, let's go x squared plus 3x plus 2. I need to figure out where does this denominator go to 0, so I need to factor it. That should always be your first thought when you look at rational functions. This factors to x plus 2, x plus 1. That means I have vertical asymptotes at x equals negative 2 and x equals negative 1. So if you were to graph this, we'll get to graphing how to graph these after a while. At negative 1 and negative 2, I would have little vertical asymptotes there. Now there is a horizontal asymptote, but that comes up on the next page here. If I had the function 1 over x minus 2, so we were talking about this just a minute ago. Vertical asymptote, x equals 2. So we go to graph. Out here at 2, you'd have a vertical asymptote. Even if it was, let's change that numerator a little bit. Even if it was 3x squared plus 6x minus 1, it would still have a vertical asymptote at x equals 2. Now there are some variations on this, but we're getting those a little bit later. But we do have an asymptote at x equals 2. All right, so vertical asymptotes are the easy ones. You need to be able to find the zeros of the denominator. Horizontal asymptotes are not hard, but they're more complex than vertical asymptotes are. There's 3 variations. The first one, we're always talking about the degree. So if I said we had x squared over x cubed, this is the degree of the numerator, the 2. The degree of the denominator is a 3. So plus x minus 1 plus x squared minus x plus 1, something like that. The degree of the numerator is 2. The degree of the denominator is 3. So if the numerator is less than the denominator, then you automatically get a horizontal asymptote of y equals 0. So that's the first one. This is n is less than d. Numerator is less than denominator, talking about degree. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So if I gave us a function that said 3x squared plus 6x minus 1 over 4x squared minus 6x plus 1, I would have a horizontal asymptote of y equals, well, this is where you got to look. My degrees are the same. They're both 2, which means it's simply this fraction of 3 over 4. It is as easy as that. That's the horizontal asymptote. But you got to remember that only is for the degrees being equal. All right. The last version here is one that we get to a little bit later, but we have to talk about it now just as a talk about. All right, so if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. But there are what we call slant asymptotes, and that's coming up over the next few days. All right, so I forgot to put this over here. This is numerator equals denominator, and this is numerator greater than denominator. Now, this just means no horizontal asymptotes. This is y equals a over b, and this is y equals 0. All right. What if I said I want to find some asymptotes? All right, so here we go. F of x equals 3x minus 1 over 2x squared plus 3x plus 1. So I need to find my vertical asymptotes, if there are any, and my horizontal asymptotes, if there are any. So horizontal is usually the fastest one because I can look at my degrees. Maybe you even know it in the top of your head already. Okay, the degree here is 1 in the numerator, 2 in the denominator. Since there's more in the denominator, a bigger degree, my horizontal asymptote is automatically y equals 0. Well, for vertical asymptotes, I like to see if this factors. And I think it does. Which means I have vertical asymptotes at both of the zeros here. So I have one at x equals -1 and one at x equals -1/2. All right, so that's my asymptotes. Let's try another one here. Let's go with g of x is equal to, let's go 4x squared minus 9 over x squared minus 2x plus 8. All right, so vertical asymptotes, horizontal asymptotes. I'm going to add something else in here. I'm going to add, hey, where are my zeros? This you might want to make a note of here in just a second. All right, so my vertical asymptotes, my horizontal asymptotes. Horizontal, pretty easy. This is a 2, this is a 2, and therefore it is the ratio of leading coefficients. So I have a leading coefficient of 4 and a leading coefficient of 1, and therefore my horizontal asymptote is y equals 4 over 1, which is 4. All right, so I need to factor my denominator here, x minus 4 and x plus 2, which tells me I have vertical asymptotes at x equals 4 and x equals -2. Now the question comes from, where do I find my zeros? Well, my zeros, like what I mean by this, by where does the g of x cross the x-axis, by the way? Okay, and g of x is going to cross the x-axis wherever the numerator is 0. So this actually factors to 2x plus 3 and 2x minus 3. And that means my zeros are going to be the point 3/2, 0 and -3/2, 0. That's where we're going to cross the x-axis. Here's some asymptotes. So eventually we're getting into graphing. You may have paid attention there a few minutes ago. That was for our section 4.2. Okay, so that finishes us off for today. That's kind of a short lesson. It's all right. Kind of straightforward. Hopefully you remember some of your Algebra 2, so it kind of might fill any blanks in that I might not have mentioned today. Here's your assignment for what we're working on tomorrow. A lot of good problems in here, a couple real-world ones in the end of this thing. So I hope that made sense for you today. I'll see you guys tomorrow. Have a good evening.